Alright, so what I'm going to do is show you guys very quickly how to solve three different kinds of projectile motion problems. This will sort of, if you can handle these three kinds of problems, you can only branch out from there and solve more difficult problems if that's the case. Give you a real quick overview. Here's a projectile being fired at 30 degrees with an initial velocity of 50 meters per second. The second kind of situation we're going to consider is a projectile fired horizontally or thrown horizontally off of the top of something, and I say, hey, if it goes so far horizontally, how high up from which it was thrown? And lastly, this one here, I say, all right, something's being thrown up at an angle. When the object is, let's say, 10 meters above the ground, how far horizontally has it went? That's the overview. Getting to the point here, in this one, if maybe the question I am trying to address is how far does this thing go in the horizontal direction? So I want to know, the x, how far does it go? All right. What we need to do first is I guess what we can do is we can look at this table and fill out what we know already. I'm not going to write units for the sake of saving on space, but I think you guys are familiar with this thing. We know the acceleration of the object in the x direction is 0. We know at the apex of the trajectory, the final velocity of the object is 0. So if I draw the trajectory here, the path the projectile takes, at its highest point, right there, I can't draw very well as you can tell, but at its highest point, halfway up from its highest point, okay? So if here's the halfway point, at its highest point, its final velocity up until that point is going to be 0, and then as we consider the second half of the problem as it's coming down, its initial velocity is going to be 0 and reach some final velocity, okay? Let's go ahead, I guess, and plug in also our accelerations in the y direction, which we know for both of these is negative 9.81. Okay, so we know that is the case there, and oh, don't do that. We also know it is the case right here as well, so negative 9.81. Yeah, don't write for me. We'll try this one more time. Right here. Negative 9.81. Okay, we're happy. That's what our table looks like under normal conditions. Now, you can see on our left that we know the initial resultant velocity is 50 meters per second. You see these little green lines I've drawn to the bottom and to the side? Those are our initial velocity vectors, because this is from where this thing's being fired. To find the bottom half of this triangle, you use the cosine function, because if 30 degrees is right here, which is what I'm trying to represent, 30 degrees is right here, this side is adjacent to that, so 50 times the cosine of 30 degrees gives you the adjacent side. Cosine of 30 degrees is radical 3 over 2, which, so we have 50 cosine 30, and that gives me about 43.3 meters per second. That's in the x direction, so I'm going to plug those values in, 43.3 there. And because there's no acceleration, the initial and final velocities in the x direction are the same. Okay? I don't know my displacement in the x direction. I'm just going to leave that blank. Nor do I know my time. I'm actually being asked to find my horizontal displacement, so we'll do that. To find the vertical component to this triangle, this is the side opposite of the angle in question over here. So we would use the sine function. So to find the opposite side, the opposite side equals 50 times the sine of 30. Sine of 30 is 1/2, so this side is 25. Where this goes? It goes into my y up column, because this is the initial velocity, vi, initial velocity, in the upward direction, so 25. Now, because this is purely parabolic and symmetric about it, it's always parabolic, but because it's symmetric, meaning I'm saying, hey, it's landing at the same I'm assuming that it lands at the same level as it started. I'm telling you it is. Because it's symmetric like that, the final velocity, just moments before it impacts the ground, is going to be the same magnitude, but different sides. So I'm going to write minus 25. Again, now, looking at my table, I don't know how high up this thing goes into the air, nor do I know how long it takes to go up. Likewise, I don't know the distance down or how long it takes to go down. And I'm ultimately wanting to know how far does it go in the horizontal direction. Okay, the way you do this, you look at these things one column at a time. So if I can get some ridiculous color and shape, I am first going to solve this thing that I just boxed in right there, the pink box. Do more dramatic effect right there. I'm solving this, okay? I know my initial velocity in the upward direction is 25, my final is 0, and my acceleration is negative 9.81. The equation that we will use to do this is Vf equals Vi plus a delta t. I can't do triangles here easily, so I'm writing it like that. If I were to plug in these numbers, I have 0 equals 25 plus a negative 9.81 times time. We do the algebra on this thing next. We could have maybe negative 25 equals negative 9.81 t. What I did is I subtracted 25 off of both sides, so I have the negatives there. If you notice, there's a negative on the left, a negative on the right. Negative over a negative is a positive. So this is really 25 equals 9.81 t. Now, to get the t by itself, I divide both sides by 9.81, and I have 25 divided by 9.81, which in terms of order of magnitudes, it's not quite 3. So if I take 25 divided by 9.81, I get 2.54. So the total time that this thing is in the air moving upward is 2.55, basically, seconds when I round up. So it takes 2.55 seconds to go up. 2.55. Which means if it takes 2.55 seconds to go up and it lands at the exact same level from which it was launched as it falls back down, that means it's going to take 2.55 seconds to go down. And when you add those values up, you get about 5.1 seconds. Total time of flight is 5.1 seconds. Now, in order to solve for the displacement in the x direction, well, that's initial velocity times change in time, according to what I call equation number 3 in class. So we take 43.3, call x equals times 5.1 and 43.3, call it 221 meters. So to solve this problem, when we do everything correctly, the ball goes 221 meters, all right? Or whatever it is that's being fired goes 221 meters, given these initial conditions. So right there is our answer. That's how you solve that one. Let's look at another one. This problem right here, same idea. However, you notice there is no y up. It only goes horizontally out and down. So what I'm going to do right now is I am just going to put a huge red X through this column. There is no y up. But let's go ahead and solve the values we do know. We do know the acceleration in the x is 0. We do know the y down is negative 9.81. I write that in there. We do know at the highest point of its trajectory, which is where it's starting from, the y direction has 0 velocity. We do know in the x direction this thing has a displacement of 50 meters, and we know its initial and final velocity in the x direction is 20 meters. To find the time, again, we're going to use the equation x equals Vi times t. In rearranging, because I want to know my time equals x over Vi. So if I plug in those values, it'd be 50 divided by 20, x over Vi, I get 2.5. I guess that makes sense, 2.5 seconds. Well, if it was moving horizontally for 2.5 seconds, since there's only 1/2 of a parabola, that also tells me it was falling through the air for 2.5 seconds as well. And if I want to know how high up it went, its displacement, well, I could use the equation displacement equals Vi time plus 1/2 times negative 9.81 times time squared. Okay, that's what my squared looks like. Well, because my initial velocity in the y direction is 0, this whole term goes away to 0. It crosses out, if you want to think of it like that. So all I'm left with is 1/2 times negative 9.81, which is basically negative 4.905, times my time, 2.5, squared. That's how I do squareds here. So 2.5 squared times negative 4.905. I get a displacement in the y direction of negative 30.66 meters. So that would be a good rough guesstimation, negative 30.66 meters. Okay, so that's my answer there. I'm happy with that. that's how you figure that out. It's negative again because it's falling down. Lastly, to do one like this, we do the same thing. Break this thing down into x and y components. Cosine of 60 degrees is 1/2, so this is 15 meters per second. We take 30 times the sine of 60 and get 26, basically, meters per second for those. So let's fill in our table now. This is 0. This is negative 9.81. This is negative 9.81. This is 0. This is 0. Here's the significance with the 10 meters. Whatever its total height is, it's going to end up 10 less than what its total is. So when I figure out how high up it goes, I can figure out what that new height is. And plugging in my y values, it's 26. This is going to be 15 and 15. If I can figure out now how long it takes to go through the air, is Vf minus Vi over A. And doing that real quick calculation, 26 divided by 9.81, my total time of flight up is 2.65 seconds. We can then figure out how high up this thing goes into the air using the third, let's use the second equation, Vf squared equals Vi squared plus 2A delta D. And if you go through doing that, 26 squared divided by 2 times 9.81, yeah, I end up with my vertical displacement being 34.5 meters, which means this vertical displacement was actually 24.5, okay? I know my time up, so let me get this out of my way. It's not to be concerned with. So it falls a negative 24.5 meters. I put the minus sign there for good measure. I solve for how long it takes to go that time using, I guess we could use the third equation, Vi delta t plus 1/2 A delta t squared. So square root of 2 times 2d over g, 4.5 divided by 9.81, gives me the time being of 2.23. So if I take 2.23 plus 2.65, I get 4.88. Now plugging this thing back into the equation, I get D equals Vi times T, and in solving what I have, I'm going to take 15 times 4.88, and I get 73.2 meters as the final answer. So I know we rushed through this a little bit, but that's how you solve those three problems.